54. In the world of high-performance distributed systems, a 54x performance penalty, that's not just a minor slowdown. We're talking about the literal difference between your application humming along beautifully and just completely collapsing under its own weight. And honestly, the surprising part is that this massive penalty is usually caused by something notoriously simple, the n+1 query problem.
Think about it. Why on earth would fetching 100 users require 101 queries? If we want to grab 100 users and their recent posts, it makes total sense to just ask the database once, right? Well, in distributed systems, the line between scaling gracefully and total catastrophic failure often starts right here at the query level. Your object relational mapper, or ORM, will often fetch those 100 users in one single query and then kind of disastrously fire off 100 separate queries just to fetch the posts for each individual user. It's a nightmare for performance. Architecting and operating high-performance distributed systems. Today, we're diving deep into exactly what it takes to build and, more importantly, maintain these massive networks at scale. Welcome to this explainer. Here's our roadmap for today. We'll start by looking at the n+1 query problem, unpack some database indexing strategies, explore caching patterns along with the CAP theorem, figure out how to tame distributed tail latency, and finally wrap up with operating reliable systems. Section 1. The n+1 query problem, a true database killer. So this is a classic anti-pattern. It looks perfectly fine in local development, right? But it absolutely destroys production. Fetching 100 users and their posts using the n+1 approach means 101 separate round trips to the database. That's taking over 800 milliseconds. But if we use a technique called eager loading, basically just a single join or in clause, we fetch the whole shebang in one go, clocking in at just 15 milliseconds. Boom. There's that 54x performance improvement we talked about. The big takeaway here? Always prioritize eager loading to batch your requests. All right, Section 2. Database indexing strategies. Let's move beyond those painful full table scans. As your datasets grow from a few thousand to literally billions of rows, scanning every single row to find what you need, that becomes fatal pretty quickly. We absolutely have to use indexes. But, not all indexes are created equal. The B tree is kind of your versatile workhorse for range and equality lookups, functioning beautifully in logarithmic time. But say we only need ultra-fast exact matches, like looking up a session ID, a hash index is going to be way faster, though it completely sacrifices the ability to do range queries. And for multi-column filters, composite indexes are incredibly powerful. It really just comes down to choosing the right tool for your specific query pattern. But hey, here's the catch, and it's a big one. Indexes are definitely not free. Every single time data is written, updated, or deleted, the database has to update those indexes too. Over time, especially in high-volume systems, this leads to dead space bloat right inside the index structure itself. Basically, our indexes degrade over time. They have to be actively maintained using operations like PostgreSQL's reindex concurrently just to rebuild them without locking up the tables. So remember, we're always trading a small write penalty up front for a massive read speed up later. Moving on to Section 3, Caching Patterns and CACP. Time for some architectural shielding. So what happens when even perfectly optimized, perfectly indexed queries just aren't fast enough? Well, we introduce caching to act as a shield for the primary database, storing frequently accessed data in ultra-fast memory, like Redis. There are really two dominant patterns here. First, with cache aside, the app checks the cache first, lazy loading from the database on a miss. But watch out, because that can cause a thundering herd if a ton of users request missing data all at the exact same time. Then there's write through, where every single write updates both the cache and the database simultaneously. This gives us strong consistency, for sure, but it adds latency to every single write operation. It's a classic trade-off. Now, distributing data across all these caches and databases introduces a harsh new reality, and it's governed by the CAP theorem. First up, we just have to accept partition tolerance. Network drops or weird communication delays between nodes, they're going to happen. It's literally a question of when, not if. Because partitions are completely unavoidable, when a failure does happen, our system is forced to make a hard choice between the other two letters, consistency or availability. Let's actually look at that trade-off. CP systems prioritize consistency. Think of a financial institution. If the network drops, the system will just reject or delay requests to ensure absolutely no one reads stale data. AP systems, on the other hand, like a social media feed, prioritize availability. They'll happily accept your request and serve data even if it's temporarily out of sync, relying on what we call eventual consistency.
It's worth noting that modern distributed SQL databases actually use some really complex consensus protocols, like Raft, to try and give us strong consistency while automatically handling failovers, keeping that availability as high as theoretically possible. Section 4. Taming distributed tail latency. We're talking about the slowest link in the chain. Okay, so we've optimized our queries, we've indexed, we've cached, we're doing great, right? But in modern microservices, a single user request might fan out and trigger up to 30,000 back-end remote procedure calls. Just look at the math on this. If a request fetches data from, say, 10 different shards, and just one of those shards has a tiny 1% chance of hitting an 80 millisecond delay, well, because the overall request has to wait for all 10 to respond, the probability of the entire request experiencing that delay skyrockets to roughly 9.6%. In distributed systems, you're literally only as fast as your absolute slowest dependency. And honestly, this is exactly why relying on average or median latency metrics is a massive trap. Averages lie. They smooth things out and hide the ugly anomalies. To expose those hidden bottlenecks in a distributed system, we absolutely have to measure the 99th and 99.9th percentiles, what we usually call the P99 and P99.9 latencies. That tells us the absolute worst experience our users are actually having. If we aren't tracking that long tail, we are completely flying blind. Finally, Section 5, Operating Reliable Systems, doing it all at hyperscale. Here's the hard truth. Even with a beautifully optimized system, hardware still fails. Cables literally get cut by backhoes. Deployments still have bugs. According to site reliability engineering principles, keeping things alive requires monitoring the 4 golden signals. That's traffic, meaning how much demand there is, errors, basically what's currently failing, latency, how long it takes to service those requests, and saturation, which is how full the system is. Observing these non-negotiable metrics is absolutely crucial to detecting anomalies before they cascade into a massive system failure. Once we have those metrics flowing, we have to set some concrete goals. An SLO, or service level objective, is your internal engineering target. That's the number that triggers your pager at 3 a.m. An SLA, the service level agreement, is the external promise we make to customers, and that's usually backed by real financial penalties if we drop the ball. By intentionally making our SLOs stricter than our SLAs, engineers essentially get a latency budget. It gives us buffer room to fix things before the business actually loses any money. There's a really powerful analogy from the pragmatic engineer that hits the nail on the head here. They say operating a distributed system is similar to operating a large organization, like a hospital. Think about it. We don't just build a hospital and walk away. It requires continuous, rigorous operations. We're talking blameless postmortems when things go wrong to find the real root causes, regular data center failover drills, and constant, never-ending capacity planning. Reliability isn't just a feature you check off a list. It is an ongoing, continuous investment. So it really leaves us with a provocative question to ask about our own systems today. Looking deeply at our queries, our indexes, our caches, and our overall operational maturity, is our distributed architecture truly resilient? Or, in the absence of rigorous testing and mechanical sympathy, have we just been lucky so far? Keep building better systems, and thanks so much for exploring this with me today.